An object with a force acting on it cannot be in equilibrium. Well, that's absolutely false. Equilibrium indicates that the forces are balanced. So you can have forces acting on an object as long as they're balanced. It's in equilibrium. Keep in mind, equilibrium means balanced forces. It means zero net force. It means no acceleration. It means constant velocity. The constant velocity could be zero or a non-zero, just the fact that it's constant. All of those things work together. They all mean the same thing. No net force, balanced forces, velocity is constant, no acceleration, equilibrium. An object with a net force must be at rest. A net force of zero. If the net force is zero, it just means the velocity is constant, like I was just going through. It doesn't mean that it's not moving. It means there's no acceleration, not no velocity. It could be no velocity, but it's not required to be no velocity. It just means net force zero means that the velocity is constant at zero or any non-zero. An object with only one force acting on it can be in equilibrium. Remember, equilibrium means balanced forces. If you have one singular force acting on an object, how would that be balanced? If one force is pushing you to the right, how are you balanced? You would need another force or forces to balance pushing you to the left. So a single force cannot be balanced. Zero forces can be, or any number greater than one can be. But a singular force would not have anything to balance it and therefore would not be in equilibrium. For the next few problems, we're going to draw the free body diagram and do the summation of forces as a part of our calculation. In the center of the free body diagram, put your mass in kilograms, and as long as these objects are near Earth, we know force of gravity is going down. If it's on a surface, we have force normal going up. And it tells us it's resting on a tabletop, so we know the forces are balanced. There's no forces in the x direction, but the net force in the y, we're going to subtract opposing forces, Fg minus force normal. They're balanced because it's at rest. At rest means constant velocity 0. Constant velocity means balanced forces. So force of gravity minus force normal equals 0. Weight is the force of gravity. Weight is, our force of gravity is calculated as mass times acceleration of gravity. In this case, mass is 10, acceleration of gravity is 10. 10 times 10 is 100. We said force of gravity minus force normal is 0, so if you add force normal to the other side, force of gravity is equal to force normal in this case, so it too is 100 newtons. Billy has a 3 kilogram notebook, so we're going to put a 3 in the box. It's near Earth, so we have force of gravity, and he presses down, so you have a force applied downward. And then it's on a table, it looks like, and so you have force normal going up. Now that notebook's not accelerating vertically, so you have balanced forces vertically. The force of gravity is still mass times acceleration, and the force applied is 5 newtons, so we know those two add up to the total downward force, and that has to equal the total upward force. So Fg plus Fa minus force normal that opposes it equals 0 because it's balanced. We said weight is Fg, which is mass times acceleration. Mass is 3, acceleration of gravity is 10. So 30 newtons is the weight. And the total downward force would be that weight of 30 plus 5. So force normal is going to have to balance that. Our net force equation did say Fg plus Fa. If we add Fn to the other side, we can say that summation is equal to Fn. 30 plus 5 is equal to Fn, or 35 is your force normal. .35 newtons. Rocky the flying squirrel is gliding from a tree, so he's coming through the air. He is not on a surface. Do not give him force normal. He's got a constant 3 meters per second. That's a constant velocity. Constant velocity means balanced forces. We don't care about that 3 right now. We care that the velocity is constant. Now the mass they gave us is in grams, so divide by 1,000 to get kilograms. So the mass is 0.2. And then it tells us that, or it asks us how much air resistance is acting on Rocky, so we know the upward force is air resistance. Nothing acting in the horizontal, so we've got force gravity minus air resistance is equal to 0. Because it's a constant velocity, we have balanced forces, so the net force is 0. Force of gravity is mass times the acceleration of gravity, or 0.2 times 10. So force of gravity will be 2 newtons. And since force of gravity and air resistance are equal to each other, air resistance is 2 newtons. Angela's playing with her 150-gram iPod before class, so we've got to put the mass is 0.15 dividing by 1,000. She's dangling it above the desk by pulling upwards on the headphones. So the headphones are attached using a cable. So any cable, string, cord, anything like that is going to be force of tension. So we have force of tension going up. She places it on the desk and pulls upward with a force of 1 newton. So it's on the desk, so it has a force normal. She's still pulling up on the cable, so she's got force tension. And she's near near Earth, so you have force of gravity down. Nothing acting horizontally. Here we can say force tension plus force normal minus force gravity equals 0. You could have just easily said force gravity minus parentheses Ft plus Fn parentheses. Since they're the same, if you subtract them either way, you still get 0. We know the weight is the force of gravity, and force of gravity is, or any force, is mass times acceleration. For force of gravity, acceleration is the acceleration of gravity, 10. Mass being 0.15 times 10, so 1.5 is the force of gravity, 1.5 newtons. They tell us that she's pulling up with a force of 1 newton, so we know the force of tension is 1 newton. So what does that leave behind for force normal? If everything has to be balanced, everything is balanced. If you've got down 1.5, what do you have up? 1.5. Well, if force tension is 1, what's left over for force normal? 0.5. Showing the calculations on the screen, so definitely follow the calculations of where it comes from, but you still have to reason out the question and decide why. What makes sense? And as long as all of these things have balanced forces, we're able to just set everything to 0 when we add up the forces. All right, watermelon, we're back to kilograms, so we don't have to do any math there. 150 kilograms, put that in the middle of your free body diagram. It's attached to a pulley that's pulling upwards, so we've got, pulleys use strings or cables or ropes, so we've got 1,000 newtons coming from the force of tension. It's not lifting off the ground, so you still have some force normal coming from the ground, and you got to find the weight and the normal force on the melon. Well, the force of gravity we know is mass times the acceleration of gravity. That acceleration of gravity, we can change and call that little g, because little g represents the acceleration of gravity. So force of gravity is really mg. We'll start abbreviating that now that we're getting comfortable with it. So mass is 150, little g is 10. So the force of gravity would be 1,500 newtons. The force of tension, they told us, is 1,000 newtons. So what's force normal? Well, we know force of tension plus force normal, subtracting the opposing force of gravity, should be 0, because it's not lifting off the ground. It's not accelerating. It's not changing the velocity, constant velocity of 0. So what's left over for force normal? Well, if we do the math, we know force tension plus force normal equals force gravity, so 1,000 plus Fn equals 1,500. So I think we can see now that force normal is going to be 500 newtons. Chef Reynolds is creating a delicious 500 grams, got to get them to kilograms, so 0.5 kilograms, pushes downward with a 2 newton force. So she's squashing that sandwich. So we've got force of gravity down, we've got the force applied down, and it's sitting on a countertop of some sort, so you've got force normal going up. That sandwich is not going to accelerate through the counter or up to the ceiling. It'd be kind of cool, kind of weird. Nothing in the horizontal. In the vertical, we've got Fg plus Fa minus Fn. I seem to add up, if they're balanced, I'll add up the the multiple side and then subtract the singular side if it has one side that has 2 and one side that has 1. But force of gravity we just said is mg. Mass is 0.5, acceleration of gravity is 10. So the force of gravity, or weight, if you prefer, is 5 newtons. Then it wants to know what the normal force is. Well, we know Fg plus Fa equals Fn because it's balanced forces. 5 plus 2 is 7 newtons. Number 10, a 3 Newton rightward force is applied to a physics notebook. So we have a force applied to the right, 3 newtons. It's going to move across the neighbor's desk. If the notebook has a mass of 0.2, so we can throw a 0.2 in the center. 0 acceleration, so that means balanced forces, right? 0 acceleration, constant velocity, balanced forces. And it says, what's the frictional force? So we know force of friction is going to the left. It's opposing to keep things balanced. Down is gravity. It's on a counter, so up is force normal. We've kind of got everything gridded out. We can say in the x direction, Fa minus Ff equals 0. That is a mistake on the video. It should say Fa minus Ff. I'll correct it in the key. And then Fg minus Fn equals 0. I'll correct that in the key as well. So hopefully you're listening to the audio. So force of friction is equal to 3 newtons because it's equal to the force applied. Number 11. 13.2 kilogram mass is placed on top of a vertical spring. The spring compresses 5.93 centimeters. Find the spring constant of the spring. How far does the same spring compress with a 17.2 kilogram mass? So first we need to know the displacement, the x. Instead of being 5.93 centimeters, we have to divide by 100 to get it into meters. So 0.0593 meters. And nothing's acting in the x direction. In the y, we've got the force of gravity minus the force of the spring. Looks like I've straightened my math back out, and that's equal to 0. Because it's balanced. We're hanging the weight on the mass, not letting it bounce back and forth, but hanging it. So we have balanced forces, right? So you have Fg down and Fs up. Well, if we know Fg is mg, and we know force of spring, we're learning right now, is the spring constant times the displacement, kx. Yes, it's negative kx, but the negative just means that the force is in the opposite direction of the displacement. For the calculations, we generally drop it, but we just need to be aware of why it's in the formula chart. So if Fg is mg and Fs is kx, and we're saying they're balanced for this problem, that means mg is kx. So if we divide both sides by x, we get mg over x is our k. Mg is 132. X is 0.0593. Divide that to the other side, and we've solved for K. Now that's the constant. It's like the strength. Think of it as the strength of that spring. It's constant for any weight that you put on that spring. That K is true for this spring. Now for the next spring, it'll be something different. But we get 2,225.97 for the spring constant. That means if we were to change out and we were to use a different weight, now this is a larger weight, instead of 13.2, it's 17.2 kilograms, that mass, it's going to sag the spring further down, right? So the displacement's going to be larger, the mass is larger, but it's still mg is equal to kx. Well, mg is going to be 172. K, we know from the previous problem, 2225.97. Solve for the new x. So 172 divided by 2,225.97, that will get us a new displacement. It'll be in meters because we measure in meters. And so since we're coming up with a pretty small number, 0.0, I think it's 77 meters. If we want to make it a little bit cleaner, we can multiply by 100 and get 7.7 centimeters. And that's a larger displacement for a larger weight. All right, number 12. A spring in a scale in the produce department of a supermarket stretches 2.5 centimeters. So 0.025 meters is our displacement, or our x. When some bananas weighing 10 newtons. Remember, weight of 10 newtons is not a mass. Weight is force of gravity. we want to know what is the mass of the bananas and what is the spring constant. Well, if we know the force of gravity, just divide by 10 and that gets you mass, because mass times 10 is force of gravity. So we're going to take the weight, force of gravity, we're going to divide by 10 and that gets us the mass. So the mass is 1 kilogram. So what is the spring constant for this spring? Remember, if we draw the free body diagram, we know that force of gravity is down, force of spring is up. If we allow it to come to a rest, it'll be balanced. Force of spring is equal to force of gravity. And if they're equal to each other, how you calculate each one can be set equal to each other. Force of gravity is mg, force of spring is kx. So mg is equal to kx. We're looking for the k. So we're going to say mg over x. Force of spring is kx. Force of spring is also mg in this case. So divide both sides by x, and it solves for k. We've got mg is 10 newtons, and then time is equal to k times x. X was at 0.025. Yes, you have to do meters. Sorry. When I calculated, I got 400. Don't worry about the units of the spring constant. A skydiver is descending at a constant speed of 120 miles per hour. Do we care about the 120 miles per hour? No. What do we care about? Constant speed. What does constant speed mean? Balanced forces. The fact that the forces are balanced, that's what we care about. And it's asking about if she experiences equal drag to 715 newtons, what is the mass of the skydiver? Well, if the drag is 715, that means since they're balanced forces, force of gravity is 715. And 715 divided by 10 would be 71.5. Because we're going backwards. 71.5 mass times 10 for gravity would be 715. A student with a mass of 70 kilograms, so we can throw a 70 in the box, into a swimming pool and sinks to the bottom. If he's sitting on the bottom, he's sitting on a surface, he has a force normal. What is his weight? Your weight is always your mass times 10. Your weight on Earth is the same. If you're in a pool or not, your weight's still the same. If the buoyant is like a floating force, so the buoyant force is going to be pushing up, and it gives us 653.33 newtons. What is his apparent weight in the water? Your apparent weight is how much you feel like you weigh, and that comes from your force normal. So it's a little trick here. Your apparent weight is your force normal. That's what they're asking for. If you think about it, if you ever get in an elevator and it starts to drop really fast, you feel weightless. And let's say it drops so fast you come off the bottom of the elevator so you don't have a force normal. So that's where you can kind of figure it out from. But your apparent weight is your force normal. We've got the force of gravity as being 700, 70 times 10. If the buoyant force is 653.33, we're looking for the force normal. And the force normal here is going to be, 46.67? So don't forget that about the apparent weight. The apparent weight is the weight that you feel. So anytime something is described as weightless, that means the force normal is 0. Or the force normal goes to 0. All right, then for each scenario, numbers 4 through 14, we need to identify if the object is at rest or traveling at a constant velocity. Now I'm going to say constant velocity, and at rest, their rest is still constant velocity, but let's go through each one. Number 4, it's resting on a tabletop, so it's at rest. Number 5, he sets the notebook down, it's at rest. Number 6, flying squirrel, constant velocity of 3. Number 7, dangling an iPod on a table, it's at rest. Number 8, giant watermelon sitting on the ground, it's at rest. Number 9, pushing down on a ham sandwich, it's at rest. Number 10, you're pushing a notebook with no acceleration, it's constant velocity. I'm using CV for constant velocity, just being lazy. Number 11, a spring is it's at rest. An object sitting on a spring, it's at rest. 12, same thing, spring, it's at rest. Number 13, skydivers descending at a constant speed, so CV. And number 14, jumps into a swimming pool, sinks down, but then sits on the bottom. He's sitting on the bottom, he's at rest. Brings us to this last problem. We're just basically using experimental design in order to determine what a spring constant is. So we just have to decide what are we going to measure, how we're going to measure, what do we need to use to measure, that sort of thing. So commonly used equipment, what would we need? We're going to use a meter stick to measure displacement, because we've talked about this in previous problems. We actually went through it in class as well. But we're going to use a meter stick to measure displacement, and displacement is signified with an x as the variable in the equation. And then we're going to use a balance or a scale in order to measure mass of the weight we're going to put onto the spring, and mass is designated as an m in the equation. I think I forget to put it initially, but later on as the video on this part goes on, you'll see I'll kind of sneak back up there and put an m in parentheses. What measurements are we going to make? We're going to measure the mass of our the attached weight. And we're going to measure the displacement of the spring from where we attach the weight, and then when it sags down, we're going to measure how far that spring is stretched. So it's an experimental design question. It just kind of helps you walk through how you would do that. And you're like, what equipment am I going to use? What measurements am I going to make? And then how would K be determined in these measurements? I'm just going to show what I'm going to do with the formula. I know that force of spring is equal to force of gravity. Force of spring is Kx. Force of gravity is mg. And so K would be mg over x, where I'm measuring m, I'm measuring x, and I know g is 10. And this is at equilibrium. It's not when it's bouncing back and forth. It's when it's allowed to come to rest. That way I can say that Fg and Fs are equal to each other. So mg is equal to kx. Again, we just drop the negative because the negative is just giving us a direction. Divide both sides by x. As long as you make those measurements, you're able to show this calculation and come up with a solution.